Tamar, who is a postdoc in Peter's group and has done a lot of really great work in reinforcement learning and planning. And starting next year, he'll be joining as an assistant professor at the Technion. And today he's here to talk to you about some of his recent work.
Thanks, Josh. Hello, everyone. I'll talk today about work I've done over the past 2 years, where the general flavor is on combining reinforcement learning with planning. And I'll try to convince you that this is a good idea. So let me start with the motivation, what I'm interested in. So I'm interested in robotics, and robots today are very good at performing repetitive tasks. For example, in the car manufacturing plant shown here. And in these tasks, the environments are usually very repetitive, very well controlled. And the standard algorithms that are used for controlling the robots in these tasks is based on classical control or classical planning, where you'd build a physical model of exactly what's going on in the task. And it might be an analytical model or computational model, and you'd solve some planning problem to get the optimal policy for it. And this works very well when everything is well controlled. But my long-term motivation is getting robots outside of these well-controlled environments and into unstructured domains like people's homes, or walking alongside humans in factories. And you can think that, a very current motivation for this is manufacturing problems where you'd have changes in the product. So for example, if you want to make a slight change to the product that you're designing, right now that would require you to re-engineer the whole control algorithm, which takes a lot of effort and time from the engineers. And if you want to move industry for better handling these types of rapid manufacturing problems, you'd want the robot to have some better autonomous decision making. So what if we want a robot to cook a meal for us or make our bed? This poses many challenges to standard methods because we have to deal with unstructured environments that can even change in time. These domains typically require to handle contact and friction as part of the solution, which means nonlinear and non-smooth dynamics, which are very hard to model. And we can assume that in many cases, a true model will never be known accurately. So you can think of the difficulty of modeling a pillow or an omelet. And finally, if we really want to get robots out there to solving these problems, we probably need much better safety guarantees or we need safety guarantees or interpretability so people will actually believe that this would work. So the first three of these challenges are very difficult for classical control methods, which rely on building accurate models of the problem. Many people now are looking at alternative approaches. And reinforcement learning is a very promising alternative, where, as you know, the agent will solve the problem not by planning in advance on a model, but through trial and error, just by maximizing some reward function. So the idea in reinforcement learning is that eventually, from this trial and error, we'll learn some mapping from the robot's observation or state to an action that leads to high reward. And by that, we kind of get around the whole problem of learning a model and solving it offline. So by definition, this addresses the challenges that we've shown before, unstructured environments, difficult dynamics, and not knowing the actual model. But in practice, we still have some challenges to overcome. One challenge that I will particularly focus on in this talk is generalization. If we learn a mapping from observation to action, if this is our result in reinforcement learning, what guarantee do we have that once we change the problem a little bit, this policy will still behave as we expect it to? So this can be a change in the environment, a change in the task, and so on. We also need to deal with high-dimensional states and actions if we want to do robotics. And eventually, we would want some safety and interpretability, which is also difficult to obtain once you're looking at the policy, which is just a deep neural network. So in this talk, the general scheme would be that we should combine these two approaches. We should combine reinforcement learning with classical planning and control architectures, so we could get the best of both worlds, both generalization and solution of difficult problems. So I'll start by presenting value iteration networks, which is a neural network architecture that has the capacity to perform some planning computation, an explicit planning computation. And we'll show that this can lead to better generalization. And then we'll show some extensions of this idea for continuous control and combining motion planning with reinforcement learning. And in the end, I'll also talk about how learning could also be used to improve standard planning algorithms. So let's start with value iteration networks. And this is joint work with Yi Wu, Garrett Thomas, Sergey Levin, and Peter Abil. So I'll get back to the motivation. We want autonomous robots. For example, we want a robot to pick up a milk for us, so it would have to open the refrigerator and identify where the milk is and grab it. So the challenge here is that the refrigerator would look different every day, so this requires generalization. And it's very easy for us, but currently way too difficult for robots. But we believe that reinforcement learning could get us there. There's very good motivation for it, because we have seen very impressive success stories of learning policies that map raw visual input to actions on complex decision-making problems. For example, in solving Atari games and object manipulation here at Berkeley. And over the last few years, there's been lots of works in this flavor. And quite surprisingly, the networks that were used for control, the policies, worked well with relatively shallow neural networks that mapped the observation to several convnet layers and then map the features of these convnet directly onto actions. So we call these networks reactive policies, in the sense that they map features of the image directly to action. And we know that these reactive policies can solve complex tasks. We've seen them work. But can they understand something? So what does it mean to understand? That's a difficult question. Let me try to answer it by a simple test that we made. And we'll interpret understanding as generalization. So in this experiment, this is probably the simplest RL domain. It's called a grid world. The agent is this red dot that needs to move on this discrete domain towards this goal without moving into the obstacles, the black obstacles. And we trained a neural network, a reactive neural network policy to solve this task. Obviously, it succeeded. This is very easy. This is way easier than Atari or robotics. But here's the thing. We then trained this policy to solve various instances of this task, random instances, where we would randomize the goal and start positions and also the obstacle locations. And now what we expect that if you train on several of these tasks and you observe a new task that you haven't seen before with different obstacles, you'd be able to solve it. This is the generalization we expect from just understanding what the task here is here, right? This is just goal-directed behavior. And for everybody here, this is easy. It requires just a glance to see what the solution should be. But surprisingly, these reactive policies really didn't generalize well. They solved all the training domains, but failed on test cases. Yeah?
So when you say we'll be able to solve the test, do you mean that you just take the pre-trained network or whatever, and then in the first run it should get there, or
yeah,
allow it for 10 more runs?
No, we don't train it any longer. We just wanted to solve it, yeah. This is the generalization that we are considering here. So at first, this surprises us a little bit. I mean, we know that these networks can solve really, really complex tasks. This is super easy. Why doesn't it generalize? But then if you think a little about it, this shouldn't be surprising at all. So what we're asking the network to solve is a sequential decision-making problem, right? If you want to solve this problem, you need to look at the goal, understand what are the sequence of actions that leads you there. This requires a planning computation. When you train reinforcement learning, you actually get around that. What you learn is just a mapping from states to good actions. How are these good actions obtained? Well, that's implicit in the training algorithm. It involves some implicit planning during training. So for example, if you're doing Q learning, then a Q value is a long-term consequence of an action, which means that you kind of account for planning while you're learning Q values. If you're doing, for example, TRPO, then you're learning advantage functions, which is similar. If you're doing imitation learning, then an expert solves a planning problem. It tells you what the good actions are, and you're just learning to imitate that. So you get planning as an implicit part of the training algorithm. And the only learning that you're doing is this thing, mapping from states to good actions. But what happens when you see a new task? You need to replan. But you never learn how to plan during RL. You learn how to map states to good actions. You have a policy. There is no reason to expect that this policy has the capacity to perform the planning computation that is required here. So now what I'll show you is a neural network that explicitly has this capacity to perform a planning computation. And we'll show that this indeed leads to better generalization. So let me describe the model. We want a network that can plan. What we know is how to map observations into actions using a reactive policy. So let's extend that by adding some planning model, which will look at the observation, decide on some planning computation to do, and decode that into actions. So first of all, we need to know what is required for computing a planning computation. How do we perform this planning? How can we actually use the plan for reactive policy? And how can we learn all of this? So we'll consider a very simple planning algorithm called value iteration. The key in value iteration is learning something called a value function, which you know is a mapping from states to their long-term value. For example, in this navigation, this could be the shortest distance to go from a state. But in general, we can talk of maximizing a sum of future rewards. And we know, this is a property of a value function, that once we compute it, it's sufficient for a reactive policy to take actions. Because an action that maximizes the value is optimal. And this is good. We would like to eventually use this for a reactive policy. How do we calculate this optimal value function? So value iteration does this iteratively. At each iteration, it goes over all the states and updates the value by maximizing the action that leads to the best immediate reward plus our current estimate of the next value. So for example, in this grid wall, this would mean that we sum the distance to the nearest neighbor plus the distance that we think is from that nearest neighbor to the goal. If we have stochastic transitions, we would need to just multiply these rewards by the probability of reaching that state. Now, I've explicitly drawn this in this particular form because this should remind you of the way we draw convolutional neural networks. And the reason is that it turns out that the computation done in value iteration is exactly the same computation that is going on in a convolutional neural network. So this expectation can actually be seen as a convolution of our current values and reward, where the convolution weights, the kernel, is just the transition probabilities. So we do this for every action that results in a hidden layer where each channel kind of corresponds to the value for a particular action. And then for getting the next value function, we need to maximize over these values, which is similar to max pooling, but only in a different direction. We maximize over the channels. We have to do this repetitively, which means that we have a recurrent convnet with shared weights, where the weights are just these transition probabilities, and each iteration corresponds to, or each layer corresponds to an iteration of value iteration. So this is very clear in this 2D navigation task, but it's actually more general because an expectation is a linear operation like convolution, and max is just like max pooling. So we'll now exploit this idea that value iteration can be coded as a particular type of convnet to design a network that can plan. So let's go back to what we had before. We know that for planning, we need rewards and transitions. We'll just have some neural network mapping from the observation into rewards and transitions. How do we plan? We just propagate these reward and transitions in the convey that we've just seen. And how do we use the plan? Well, we know that the value function is sufficient for making optimal actions. So we'll just take the value function that we got, feed it to our reactive policy's additional features. Now the reactive policy has all the information it needs to potentially take the optimal action. So now how do we train this network? We can train each component separately because it's just a neural network. But that would require supervision for each one. Instead, and this is what we'll do here, is just treat the whole network as one very deep neural network that we can train end to end. And let's think about what this would mean, training it end to end. What we would learn is mapping the observation to some rewards and transitions that once we do planning on these rewards and transitions, this leads to useful actions. And we'll learn everything just end to end, either reinforcement learning or supervised learning. So let's see how this works. So let's go back to this grid world example we've seen before. And we trained this using supervised learning just so that exploration wouldn't be a factor in the result. That means that we compute the shortest path. This is easy from the object to the goal. And we feed that as expert of demonstrations. We compare value iteration networks, or VINs in short, with standard reactive networks that we're using in the literature. For example, a convey that is similar to the one used in the DQN architecture, and a fully convolutional neural network, which comes from image segmentation. And you can think about this problem as kind of an image segmentation task, where each pixel, the action in each pixel corresponds to the semantic label. So here are the results of the train. This is a supervised learning problem, so you can just measure the training prediction error and test prediction error. And what you see here is that, well, as we expect, as the domain size increases, the prediction error gets larger. This is not surprising. And all the networks seem to do relatively the same here. But here's the interesting thing. Once you actually look at the interesting, or what we care about, what is the success of this neural network when applied to a new problem? Does it actually reach the goal or not? You see that these reactive networks really decrease in performance once the network size the problem size increases, while value iteration networks kind of maintain a steady performance rate. And what turns to happens here is that these networks, the reactive networks, just learn to memorize what they've seen before. And this works well on small problems, but definitely doesn't scale up once the problem size increases. So value iteration networks, on the other hand, learn the actual planning computation that's required to solve a new task. Here's an example of what it produced. Red is the trajectory that the value iteration network produced, while blue is the actual shortest path. It doesn't learn the actual shortest path, but a relatively short path that leads to the goal. So it really learned to encode the goal-directed behavior here. We can also interpret what this network learned. Because we have a planning computation, we understand what rewards and transitions mean. So we can look at the reward that it learned for this particular map. And what you see here is that it learned to put a high reward at the goal, which is expected, a negative reward on obstacle, which is also expected, and a very small negative reward on free space, which induces a short path to the goal around the obstacles. So this was learned from scratch. It never learned that this is something that it needs. We can also look at the value that is induced by this reward, and you see that it's high at the goal and navigates, the gradient of this value goes around the obstacles to the goal. So one thing you can ask is, well, we've seen that we've transformed this planning into just a deep convnet. So do we actually need a structure of value iteration? Can we just take a deep convnet instead? It's much deeper than the reactive baselines. So we try this by just untying the weights in the value iteration networks, which just makes it a deep convnet. And this worked worse, especially with less data. So the actual structure was important here. We can also train this using reinforcement learning. This is an example using TRPO. We needed to use a curriculum learning here for it to solve or to reach the goal in the challenging tasks. But you see that, again, the VINs were much better than the reactive baselines. But here's the nice thing about VINs. It's just a neural network. So you can compose it with more complex models for example, perception and control. Here's an example where instead of this synthetic grid worlds, we wanted to solve navigation on image-like domains. So this is Mars. This is an image from a Mars terrain. We wanted to navigate around these craters. Only thing we needed to change is the perception model from these observations into the reward. We added a bit more conv layers. And here in purple is the line, the trajectory that it predicted. For continuous control, we can also use this. Here's a domain of navigating between these obstacles. Now, this is continuous, and you might ask, how can we represent discrete planning in value iteration in a continuous domain? Our idea was to kind of let the network figure it out by training end-to-end. So we still used a discrete 2D grid world for planning. And the result of this planning, the value in this planning, was fed to a reactive policy, which also took as input the continuous state. So now it has the capacity to kind of plan a high-level trajectory in this discrete grid world and execute it on this continuous, or follow it on the continuous domain. Here's well, we compared it again to reactive baselines. We do much better. Here's an example of how this looks like. This is a network predicting actions on domains that it has never seen before. And you see that it generalized quite well. It captured the idea of moving to the goal between obstacles. Not always it succeeded, but most of the time.
How does using continuous domains affect the training time?
Well, we trained this using a different algorithm. So this is trained using GPS. It's a completely different training algorithm, but you can train this using TRPO or something like that. We haven't tried that. So VINs are quite general. In fact, we've used them to also solve navigation or navigating website links to find a natural language query by doing the planning on graphs instead of grids. And you can also compose VINs hierarchically by feeding a value function of one VIN as an additional input to a higher level decision-making VIN. Here's an application of this idea from a group led by Saurabh Gupta from Chandra Malik's group. And they use this hierarchical VINs as part of their network for learning to navigate from a first-person view. So obviously what we've seen before can also only be used when you have the full information in your observation. For example, an overhead view of the map. If you have a first-person view, you also need some memory to remember what you've seen and to actually code it into a map. And this is what they did. They combined a mapping model, differentiable mapping model, with a differentiable planner based on a hierarchical value iteration network. And here's the result of their model navigating from first-person view an unseen building. And I think this is pretty cool. It's reaching the door handle, I think. So to summarize this part of the talk, we've seen that by learning to plan, we can get better generalization in sequential tasks. And this is going to be the main story in this talk. In particular, we've proposed a framework that has an explicit planning component in the neural network architecture. We've seen that it can be used for different problems. And I think the main takeaway is that a deep network structured appropriately has the computational capacity to perform some planning computation. And this is, I think, the take-home message here. The challenges with value iteration networks, this explicit representation, is that value iteration can work well on small state spaces. This doesn't really scale up to high-dimensional spaces like in robotics, because, well, you can discretize, but you can't discretize something that is 7-dimensional, for example. So in the next part of the talk, I'll show different approaches that really do scale up to these high-dimensional spaces required for robotics. We'll start with our work on hindsight MPC. And this is work with Garrett Thomas, Tianhao Zhang, Sergey Levin, and Peter Abil. The motivation, as I said before, we want to scale up this approach to robotics, particularly robotic manipulation, for example, assembling these gears objects that you see here. The challenge in these tasks is that we can't get an accurate dynamics model because it involves contacts and frictions, which is very hard to model. We build on a very successful standard control method called model predictive control, which has recently been used for manipulation successfully in several papers. And before I get into the details, let me explain how model predictive control works. So the idea in model predictive control is that at each time step, we'll solve a short horizon version of the problem. So for example, when we are at time t and our state is xt, we'll try to solve the optimal policy for time steps xt plus 1 until xt plus h, where h would be the horizon of the algorithm. We'll maintain some model of the dynamics, which won't be accurate, but we'll improve it as we go along. This would be this model ft. Now, how do we solve this optimal problem? One way is to linearize the dynamics model that we have around the trajectory we predict, and then solve a linear quadratic regulator, which you've already seen in this course. We can solve when we have linear dynamics and a quadratic cost function. So we're going to assume that our cost function is quadratic here, and what we get is this optimal control formulation. Notice that the horizon here is h, and you've seen this is an LQR. We know how to write down the solution for this using dynamic programming. So that means iteratively going from the last state to the first state and computing these matrices and multiplications and inversions. This gives us the optimal policy for the h-step horizon under these linearized dynamics. Now what we do in MPC is we only take the first action in this policy, apply it, and then repeat the whole process again. Again, we'll linearize the dynamics, solve the optimal policy, and so on and so on. So you can think of it as kind of an online version of iterative LQR. MPC is well used in robotics. It has many applications. It works really well, but it still has some suboptimality. It results from two facts. One is that we only use a finite horizon in a computation, while what we actually care about is the full horizon. And also because our dynamics model, or our prediction, is not correct, because we are learning the model as we go along. And typically, the horizon that people use is very, very small. The reason is both for computation feasibility. We need to actually solve the LQR problem online, but also because if we have errors in the model, there's just no reason to plan too much into the future. So in this work, what we ask is, given that we can perform the same task over and over again, how can we improve this MPC method? So one straightforward thing to do is that after you solve the task multiple times, you get more data. So you can improve your model. And we tried that, but that really didn't help much. So now I'll describe a different approach, which we call the hindsight planning. And the idea is that after you've seen what really happened in the world, you can go back and ask yourself at each time step, what should I have planned instead of what I did to get better actions? So let's see how this works. Let's go back, revisit the planning that we did at time step t, but now after we've seen how the whole trajectory actually turned out. So now we can perform the same planning computation that we did before, but now we can linearize on the actual trajectory that we've seen and not on some predictions that we needed to predict before because we didn't know this. This will already improve the accuracy. But also we can use a longer planning horizon because now we are doing this offline. We're not limited by any computational constraints. So we'll solve a longer planning horizon, again with the same LQR computation. And after doing this, we'll get what we call the hindsight action, U bar. This is what we would have acted at time step t if we knew what we knew at the end of the trajectory. We can perform this for every action in the trajectory, which results in what we call the hindsight plan. So this hindsight plan mitigates the two suboptimality factors that I described. The prediction error, because we're predicting on the actual, we're linearizing on the actual trajectory, and the short horizon. So in principle, these hindsight actions are better than the actions that we took. But now the question is, once we run the MPC policy in the next episode, we're still going to be limited by the short planning horizon and the predictions. So how can we actually improve this online MPC method? So here's the idea. We're going to change the cost of MPC such that a short horizon online MPC would behave or mimic these hindsight actions that we've computed offline. Yeah.
Can you clarify a little bit? It seems like there's multiple ways of getting the hindsight actions. If you go starting from the initial time step and then keeping what happened to the trajectory fixed, what was the best action in that first time step, or you could go the other way and then you would have to have best action in hindsight, but then you would keep the new hindsight actions ahead of you. I guess
the trajectory is already seen.
Mm-hmm.
We cannot change the trajectory.
So you would be, each time step would be optimizing the action subject to the rest of the trajectory being the same.
Yes, exactly.
What do you do on the second, on T+1? Do you have the new action or do you keep
on T+1, we'll still use the same trajectory, like this had never changed.
In principle, this could be done in parallel for every action.
Yes, exactly, yeah. You're right that potentially once we change this action, this trajectory changes. Mm-hmm. But the idea is that this would still be better than the prediction that we had before where we don't have this at all. So to get an intuition where this would work well is, for example, if a contact happened, for example, at some time step, it's very hard to predict contacts in advance. But once you've seen them, you know that the dynamics model changed. All right, so let's see how we do this in practice. We assume that our cost function is some quadratic structure of quadratic distance to some goal x star. This is the original cost function. We're going to add a shaping to this cost function where this goal would be the output of some neural network that takes as input the current state with some parameters theta. The idea here is that by changing the goal along the way, we can kind of learn something like waypoints. We would learn these goals automatically, of course. And this goes back to the idea where we had invalid iteration networks, where the whole model is going to be a neural network that takes as input the observation, has some black box neural network that computes these goals, and that gets passed to some differentiable planning algorithm, which in this case is going to be this LQR planning. And this will compute the control. So how do we learn from the hindsight plan? Well, we can pose a standard supervised learning problem. we'll minimize this loss. The first term in this loss is the actions that a neural network, or that LQR with a cost function with a neural network parameters theta would have taken. The second term is just the hindsight actions that we already computed. So this looks pretty simple. This would make the cost function motivate actions that are like the hindsight plan. Yeah?
How does this work, I mean, in a high-dimensional setting where you would, even if you have a hindsight action, like, I guess, the closest previously visited state on a previous rollout would still be pretty far away from, like, any state you could expect to see in a new trajectory. Like just, like Kirschner dimensionality-wise, if you're, like if you have a low probability of visiting the same state twice, like ever.
Well, there is an assumption here that this neural network is going to be smooth. So there's a smoothness assumption implicit here. The trajectories are going not to be exactly the same, but similar enough that some information from the previous trajectory is actually useful for it.
Okay.
This is the...
I guess that makes sense, yeah.
All right, so let's talk about this objective for a second. It looks pretty simple, but actually, to minimize it, we need to differentiate through the whole dynamic programming LQR calculation that we saw before, the whole matrix inversions and multiplications. This seems complicated, but actually, once we write it down in Theano or TensorFlow or any AutoDiff program, this just becomes another type of neural network. And this is what we're actually exploiting here. So let's see how this works. And we'll start with some illustrative example. So here, this is a task of moving this yellow particle throughout this opening into a goal. So what do we expect MPC to do? This is the line in red. Because the horizon is short, in the beginning, it doesn't know about the goal, the obstacle in advance, so it just shoots towards the goal. And then once it hits it, it learns to kind of go around it. What we expect to learn is a direct movement towards the goal that accounts for this obstacle already in the beginning. So here's our algorithm. We start by showing the MPC baseline. As we expect, it directly shoots towards the goal and then only then goes around the opening. And then the hindsight planning, very quickly, within 3 iterations, you would see that it learns to go directly through the opening towards the goal. So this is a kind of a simple task. We've also shown this on a simulated peg insertion task. Here the space is much larger. If you account for all the joints and velocities and the end effector positions and velocities, you result in 26 dimensions. This is a 7 degree of freedom arm. And we used the dynamics we are based on Gaussian mixture models. And we compare our method with ILQG, which is a state-of-the-art method. ILQG eventually solved the task, but our hindsight MPC solves it much quicker. The reason it solves it much quicker is that, well, we started from MPC being a very good control method. This was the prior assumption. And even in the first iteration, you see that it does better than ILQG. What we show is that we can also quickly improve it to reach a level almost as good as ILQG in the end. You can think of ILQG as being the optimal solution here in that it accounts for the whole horizon, the full horizon. We also compared the red line here is just the standard MPC, which, well, you see that we dramatically improve over it. Here's how it looks on Real Robot. This is, again, a similar peg insertion task like you saw in the 2D toy task. And you see that the MPC baseline will, first of all, kind of hits this plate while inserting the peg. And what we learned is a smooth trajectory that directly goes towards the goal.
What's standard MPC?
Standard MPC.
What is it using to plan?
To what?
So, like, you say it's the baseline. What does that mean?
MPC doesn't use the hindsight planning to adopt the cost function.
So this is just ILQR then?
It's not ILQR. This is, at each time step, it would compute an LQR policy and apply the first action and recompute.
Okay.
ILQR would learn the dynamics and solve for the full horizon. This would be the other baseline. All right, so to summarize this part of the talk, and going back also to iteration networks, well, we have seen decades of research on planning and control algorithms, and we've seen a method to include this knowledge as part of the neural network structure as some kind of inductive bias. And I think this provides a more principled approach to designing neural networks for control, because we're using design decisions that are specifically tuned for these types of problems. And in general, we've seen that planning can actually be used to help learning, either for generalization or for speeding it up. And now I'll discuss another idea of using planning to help reinforcement learning. And this is joint work with Garrett Thomas, Melissa Chian, Juan Aparicio Egea, Peter Bill. So the motivation for this work is similar to what we've seen before. We want to solve robotic assembly problems. And the challenge in these robotic assembly problems is that the physical model that we have is very complex, or that we don't have is very complex. The reason is that we need to account for friction and contacts, and this depends on the way we actually manufacture these parts, and we don't really have a good way of knowing that in advance. On the other hand, in practice, in many of these problems, a geometric model of the problem is readily available, because the designer that actually designed these parts had a CAD model. We use a CAD software, so we can easily assume that we have access to geometric information. So in this work, we wanted to ask, can we exploit this geometric data using motion planning and combine that with reinforcement learning to get the best of both worlds? So let me specify exactly what the problem is that we're trying to solve, or why do we need both motion planning and RL. So let's think of the task of assembling this ring on this peg. So it's very clear what the solution should look like. And a standard motion planning algorithm, a geometrical motion planning algorithm, would easily tell you that the motion should go above it and place a ring on this peg. That's OK. But then, once you have this plan, you actually need to execute it on a real robot. Now, we need to apply actions that will move this ring along this trajectory, which is not that trivial if this fit is very tight. So for example, if it's a very tight fit and you're approaching it a little bit misaligned, then you need to understand that the correct action is to realign it on the center of this peg and not to keep going downwards. And a standard tracking controller, for example, will not know that. On the other hand, you can go RL at it and just feed it to some magic RL policy optimization algorithm and expect that it will solve this problem automatically. It would if this peg is very short. But then if you increase the height of this peg, the probability that random exploration will discover that you need to actually go above it and insert it to reach the task, to reach the goal, is close to 0. What you expect us to learn is just to move it alongside the peg to minimize some cost function. Really not what we want here. So what we would like, or what we propose, is to combine these methods. We'll use motion planning to get kind of the high-level geometric trajectory, and we'd use reinforcement learning to account for all the problems that we have with dynamics. How do we do this? Very simply, let's denote by X reference the trajectory in state space that motion planning gave us. We'll treat it as a reference trajectory, and we'll design a reward function that just tries to stay as close as possible to this reference trajectory. For example, the square distance to it. Now here's the thing. If you run this cost function in RL, RL tries to minimize the sum of these costs along the trajectory. So this means that if at some point it's beneficial to stray away from the trajectory, that in the future you would get close to it, RL is expected to find it. So let me tell you about the system we designed. So the system starts off with the robot, or we start by having some CAD models of the objects that we want to assemble. We use a robot perception to know, or we just attach tags, to localize these objects in the actual scene. And we have some goal state that is predefined. For pose estimation, we just use standard tags. The robot perception is the joints and end effector positions in this work. And then once we have that, this is enough information for a standard motion planning algorithm for computing this trajectory. We used OMPL as motion planning here. And once we have this motion plan, we can feed it as additional information or as a reward function for policy search. Here we used iterative LQG. So we use it both for the reward function in LQG, but also for initializing the policy. So you can easily initialize a linear policy in LQG as a PD controller for tracking this motion plan, which also speeds it up considerably. We tested this idea on several challenging assembly tasks. So this is assembling this peg into this hole. This is assembling this gear onto this shaft. And this is assembling these two U-shaped objects. Now, the tolerance in each of these tasks was less than 1 millimeter, which is very challenging for the PR2 robot that we're using. Also, this U-shaped task requires a complicated assembly task. It's just, if this, for example, piece starts to the right of this piece, you need to learn how to rotate it and put it in the actual correct position for insertion. These are things that standard RL is not expected to find easily. Also, motion planning, because of this low tolerance, would not be easy to actually execute. And we see that, indeed, our method that combines motion planning with ILQG solved almost all of these tasks successfully, while standard motion planning that used the exact same motion plan didn't solve them, and also neither did ILQG. And here's a video of this. What you see here is that this is first the standard motion planning with a PID controller to track it. And you see that because of, let me stop it for a second. Show this again. So as we expected, because of some inaccuracies in the state estimation, the robot doesn't know how to fix tracking the controller once it's made an error. Next, we see the ILQG, which is as we expected. It doesn't learn that it needs to first go above the hole and insert it. It just tries to stay as close as possible to the target location, which obviously is not what we want. Again, ILQG failing. And this is ILQG with the motion plan as I've described. You see that it both tracks the correct trajectory, but also manages to get around these difficult dynamics once the peg is inserted. It also learns really fast because we're using the PD controller to initialize learning. So the whole learning time is in the order of 30 minutes, something like that, within 5 iterations of ILQG. So this was good. From a fixed initial position, we can solve challenging assembly problems. But what happens if we change the initial position, for example? Then we need to learn from scratch because our whole motion plan and controller is not good anymore. So we can train the policy in a set of initial positions and feed it to some neural network controller to try to mimic these controls, with the hope that this neural network will learn to solve the problem for multiple sets of initial positions. This is standard to the work done in the GPS works. But here's the thing, if you train a standard neural network controller, there's not really hope that it would learn to mimic the complex decision making that the motion planner is doing. Instead, our idea is to design a neural network that takes as input both the states of the robot and a motion plan that we can compute, and a reference trajectory. And what this neural network learns is just how to track this motion plan. And the idea is that we feed in the whole reference trajectory to the neural network, and we compute an attention over the current part of the trajectory that is most relevant to our current state that we want to track. For example, if this is the current state and this is the trajectory, we feed in a window of the most recent observation or most recent states in the motion plan, and we learn a soft attention model over this window. And what this learns to do is to track a motion plan that it hasn't seen before. And here's an example, an experiment we did, where we trained this on a set of 10 initial configurations of this part. The white parts are the different initial configurations. And you see that each initial configuration could require a very different motion trajectory, requiring different rotations, which is not something that you would expect a standard neural network that does some interpolation to generalize over. And what we tested is very different initial positions. And we see that this method could get 90% accuracy both in the training and in the test domains. And here's how it looks in practice. The green is the motion plan. And what you see is a neural network that has learned to just track this motion plan from various initial positions. So far we've seen different ways of using planning, conventional planning, to increase the performance and generalization of reinforcement learning. But can we also go the other way around? Can learning improve planning? So this is the next part of this talk. And this is work with Eddie Groshev, Max Goldstein, Sid Srivastava, and Peter Abil. So in this part of the talk, we are going to forget about robotics for a second and focus on deterministic task planning domains. So this is, let me show you some examples of what this looks like. Here, this is the Sokoban game. In Sokoban, there is this grid world, and the agent in red needs to move this purple particle to the green goal position. But it can only push this object, the purple object. So this means that it requires kind of complicated maneuvers to actually move it around. You can try to see, this is a particularly challenging domain. You can see that it requires some thought about what would be the trajectory for reaching it to the goal. It would start like this, moving it to this point, and you see if you can figure out how it continues. Another classical problem is a traveling salesman problem, where there is a graph of cities with distances between them, and you need to find the trajectory that visits all of these cities in the minimum distance. Now, these problems have been there for a long time. They have different models of specifying them, for example, PDDL or MDPs or strips for planning. And a planning algorithm is typically a manually designed algorithm that takes in the problem as one of these definitions and outputs a policy, where the policy is just a mapping of what we want to do, either states to actions or a list of actions that we'll encounter in the future. This is deterministic, so there is no stochasticity. So there is a lot of research in these, on these problems, but we know that these problems are, in general, hard. And what we ask here is what if several different planning problems come from a set of similar problems or a domain of similar problems? And we pose this as a learning problem. We want to have a set of training problems. For example, problems could be different levels in this Sokoban game that I showed you before. And we want to plan on this training set so that we will improve planning on a test set from the same domain. So this is an old idea. It's called learning to plan. And there's many approaches to it in the planning community. But the main difficulty has been that it's very hard to find a good representation of what to learn. So people have looked at mapping the PDDL description of the problem to some policy, or learning sub-goals or options and things like that. It's not clear for a given problem what is the actual useful representation for it. So we'll try to use recent advances in deep learning and representation learning to use experience to plan faster. And the idea is actually very simple. We'll define something called a generalized reactive policy, which is a complex name for just a neural network that takes as input a current observation of the game and some goal observation that we want to reach, and outputs an action. Very similar to a standard policy, or something called, in reinforcement learning, a universal policy sometimes, because it takes as input the goal. And the assumption here is that thus observations contain enough information about the problems that we can actually compute a good action for it. And the way we train these reactive policies, or GRPs, is just by behavioral cloning, or imitation learning. That is, we have a set of training problems. We generate them. We solve each one of the training problems using a state-of-the-art planner that gives us a policy of observations and actions, a data set. And we train this neural network from these observations to produce the correct actions that the planner gave us. This is very similar to the setting that we had in value iteration networks, only here we won't consider our value iteration networks because these problems are too difficult to solve using value iteration. So now the questions are, what is a good architecture for this? Can we actually learn non-trivial GRPs? Does this generalize to different problem sizes? And can we use the GRPs that we have learned to improve standard planning? So let me tell you a bit about the architectures that we used. This is motivated by value iteration networks, where we saw that a deep network can encode some planning computation. We had the reward fed in at each time step for the value iteration computation. And this is similar to kind of a skip connection from the input observations to each layer. So the way this works is we feed in this observation to a set of convolutions, deep convnet. We had 14 layers. The observation is fed as to each one of these layers additionally as a skip connection. And this eventually goes to a fully connected layer for predicting the action probabilities. We can also add some auxiliary predictions here, for example, the plan length, which improve performance somewhat. For the TSP problems, the problems there were recorded as a graph. So in this graph, each node has 3 features. The first one is a binary feature where this is the current node visited by the agent. The second one is whether this node has been visited before. And the third one is whether the agent started from this node or not. So using these 3 binary features for each node, we can represent the whole state of the problem. And in general, you can think that many planning problems on graphs can be represented in this way, using some features for each node. And we do the same thing. We have convolutions. This time it's graph convolutions over these features with skip connections from this observation to each layer. And this later results in a fully connected layer for action probabilities. So the idea is that, well, we know that convolution networks can learn very good representations of problems. We'd like to use these good representations for learning or to plan. So does this work? Well, here's the network that was learned for Sokoban using 9,000 training domains. And this is a network predicting actions for a domain that it is never seen before. And you can see that it learned, well, quite a complex policy that needs to look ahead many time steps in the future for the current action. This really shows long horizon planning learned by the network. In terms of numbers, for one object Sokoban, we get 97% success, and for two objects, we can get to 87% success. I think this video shows kind of the quality of and difficulty of these problems. So now you might think, well, I can get to 97 or 87 or some number in between. How good is that? Maybe I want 100% success rate. So what we've shown is that you can use the same neural network that was trained for predicting actions as a heuristic function in A-star search. And this guarantees 100% success. And we show that this is much, much faster than using standard heuristics in A-star. So I'll show you the numbers. So this figure is a bit confusing. Let me explain. Let's first look at the boxed areas. So what this shows is for Sokoban trained on 9x9 domains and tested on 9x9 domains. This is the number of state explored during search, which is a measure of the time it takes to plan. And this graph shows the performance, the length of the plan that was found. So shorter is better. So we compare, for example, A-star with the neural network heuristic in blue with FD, which is an optimal planner for this case. So you see that we are orders of magnitude faster with a very noticeable performance loss. If you compare to A-star with a standard heuristic, this is the Manhattan heuristic used for Sokoban, we see that we again are order of magnitude faster, though very similar very similar quality of the plans that we produce. So this shows that the neural network really captured some underlying structure in the problem, because when we use it with planning, we get much better results. Now we can ask about generalization. We can take the neural network that was trained on 9x9 domains and test it on larger domains. This is 12x12 and up to 18x18. And what you see is that, well, the blue line here, it takes more and more time compared to the standard planners, which means that this structure that we learned gets less and less useful. But still, we are orders of magnitude better than, for example, the optimal planner, and the quality of the solution really doesn't degrade much. So this shows that we're able to learn good structure in the problem that actually generalizes. So now you can ask, well, if we can do that, maybe we could start by learning on simple problems and use the knowledge that we learned to make planning faster on larger problems and continue to improve this, like a curriculum learning style. And this is something we explored in an algorithm that we call leapfrogging. And the idea is as follows. We start by small problems of size k, and we'll solve them using an optimal planner that takes a long, long time. And we'll get the optimal plans for those problems. This is easy if these problems are small. And we don't want to use this optimal planner anymore because it takes a long time. So what we'll do is we'll train a GRP for this set of problems, and then we'll generate a new set of problems with a larger size, k prime, and we'll solve these problems using A-star plus the GRP that we've trained. And now we've seen that this solves these problems much, much faster and generalizes to these larger problem sets. So now we have new data for a larger planning problem, and we can use it to, again, train another GRP, solve problems from even larger size, and again, use it in A star and generate more data, and so on and so on and so on. Now we can solve problems of a large size with only using the slow planner for very small problems. And here's how this works in practice. Let's only look at the green and yellow lines. The green line, this is for a traveling salesman problem trained on 4x4 graphs. And we evaluated on graphs of size 5 to 12. And green is the standard neural network that we've seen before. It generalizes, but not really well. Shorter here is better. And this yellow line shows this leapfrogging algorithm, which at least for up to problems of size 9 has almost no loss in performance because the data that we regenerated was useful for retraining the GRP. So let me conclude this talk. The idea was that by involving planning in learning, we can get better generalization. Before I present a specific conclusions, let me say that there's other ways of tackling the generalization problem in reinforcement learning. Let me show a collection of some recent works that are relevant from different angles. So another way of tackling generalization directly is using meta-learning, where here you would specifically learn on a set of different tasks or task instances. And you can do this by, for example, RL squared, which trains a new, recurrent neural network to quickly solve a new problem, or by MAML, model agnostic meta-learning, which is another way of doing this thing. Another idea for generalization is using successor representations. The idea in successor representations is that the only thing that changes between domains is the reward function. So there's a trick that you can learn features that encompass all the dynamics of the problem. And once you have a new reward function, you just project this reward function onto these features and get immediately the optimal policy. There's some recent work on that. It's a very interesting recent works that combine planning within the neural network architecture. So these three works, value prediction networks, imagination augmented agents from DeepMind, and TreeQN and A3C, use, instead of value iteration, which does backward planning that requires to go over all the states, these do forward planning. They learn a forward model, an implicit forward model of the dynamics, and plan using a tree search on this forward model. There's also the predictron from DeepMind, which uses a similar idea just for value function evaluation. And finally, there's some recent works that do different combinations, interesting combinations of planning and learning. Schema networks is a very interesting work which learns kind of a graphical model of change of features in the environment and uses graphical model inference for doing the planning on that. And a recent work on Go from DeepMind, mastering the game of Go without human knowledge. This is AlphaGo 0. Uses some kind of Monte Carlo research combined with reinforcement learning and a lot of other things to really get amazing results. So to summarize, planning in principle can get us better generalization and also some interpretability, because usually a planning algorithm is easy to interpret. So I hope this motivates you to think beyond reactive policies in reinforcement learning, think more about the structure or different types of algorithms that we combine with the reinforcement learning problem. What's next? So several things that we are interested in is different types of planning, for example, motion planning and assembly planning. This would really make these ideas work in real robotics domains. Also, the idea of generalizing from simple to hard tasks is something that is very interesting. I think if you look at, for example, AlphaGo 0, one reason that it was so successful is that once you're training against an opponent, you have a natural curriculum of starting from simple problems and gradually increasing the difficulty as the agent learns. We don't have that yet for goal-directed planning, like the problems that I've showed here. But maybe the leapfrogging algorithm that we've shown could be a way to tackle that. Another interesting thing is, right now we're using the planner as kind of a fixed component. For example, in the motion planning NRL work. You can also think of how we can adapt the planner to better guide reinforcement learning. And finally, using a planning algorithm could be an easy way of adding safety constraints to our learned policy. Thank you. I'd like to also thank all my collaborators and funding agents.
Do we have any questions?
Yeah.
Can you share your slides?
Sure.
And I was actually, the last stuff you did with the Sokoban, I was actually trying to find it on my computer while you're talking. Is it up on?
It's on archive. That work is on archive. I'll put a link to it.
Okay, great, thank you.
So
Yes.
how will that solve ESP, cavity fill-man?
So the graph here, well, this was trained on 4x4, but you can see that on 5x5, this is the difference compared to optimal. So it's within 5%. This is even on generalization. So on the same, on problems from the domain that it was trained on, it was less than 5% of optimal.
But it always finds like
It always finds, it always finds the corrector.
But domain, you mean the random graph generating process is the same?
Domain, I mean the size of the graph, the number of nodes in the graph. The way we generated these graphs, we tried two types. One was just a fully connected graph with random weights. The other was taking a cycle and adding connections within the cycle between random nodes, making it a much sparser graph.
Okay.
So, and this was from the same domain.
Okay, but which one of those two was this?
So this is showing, not sure. Yeah, this is with the cycle with adding random connections between it. Yeah. Yes.
Have you tried policy iteration-based planning, or like for example, like policy iteration?
No, the reason is that policy iteration requires you to take an argmax, and it's harder to differentiate through that. Right? It's harder to present that as a differentiable computation, but probably it can be done in some way.
Okay, if we have no further questions, let's thank the speaker one more time.